Hey there! Welcome to this introduction on how to use deepBlink. I'm Bastian and I created deepBlink together with Zan. This introduction is broken down into 5 sections, which cover the topics of installation, labeling, training, downloading models, as well as prediction. Feel free to skip ahead to any of these sections by clicking the links in the description below. We hope you enjoy.
Before we begin, note that these videos won't give any instruction on Python or basic command line usage such as cd or ls. Please check out the links in the description if you aren't familiar with the terminal. deepBlink is written in Python. The easiest way to install Python is through Anaconda. Anaconda is an open source distribution that simplifies managing Python packages. Additional information about Anaconda is in the description. Go to Anaconda's official website, click on Download, and select the graphical installer for your operating system, which in my case was macOS. Once downloaded, follow the instructions as indicated on the screen. Now, go ahead and open up the terminal or the Anaconda prompt on Windows. If everything went according to plan, you should be greeted with a base Conda environment in the terminal. All you need to know for now is that an environment is a collection of packages. We will create a new Conda environment by typing conda create --name deepBlink Python equals 3.7. This just created a new Conda environment with the name deepBlink and Python version 3.7. Every time you want to use this environment, we have to activate it by typing conda activate and the name of the environment, which in our case is deepBlink. You will notice that the environment indicator now is showing that we are indeed in the environment deepBlink. The last step will be to install deepBlink by typing pip install deepBlink. This automatically downloads deepBlink from Python's packaging index PyPI. Check your installation by typing deepBlink help, which opens up the man page for deepBlink. 2 notes. All subcommands such as deepBlink check or deepBlink config have their own help page by typing deepBlink plus the command --help. If you want to know more about what is going on under the hood, you can change the execution modes to verbose by adding a -v or --verbose flag after the normal command. If you want to train your own model with custom data, you will need to label images. The number of images required will vary depending on the uniformity of your data. In previous experiments, we found that around 200 example images was enough for decent performance. Labeling is performed in Fiji, where we will use the TrackMate plugin. If you haven't installed TrackMate, go ahead and check out the description below. Repeat the following steps for all of your images. First, open up one of your images in Fiji. You can use plus or minus to zoom in and out of your image. Then, launch TrackMate. Next, start the base detector and play around with the values until most spots are detected by clicking on Preview. If some spots weren't or falsely detected, you can use the keyboard shortcuts D to delete, A to add, or space and drag to move a spot. Finally, export the detections by shift-clicking on Analysis and save using the same name as your original image. Just don't forget to change the extension to CSV. Now, repeat this process for all of your images. This might take a while, so we suggest to listening to something fun. Once complete, in your folder you should have a bunch of images and all of their corresponding CSV labels. We will now use deepBlink create to create an NPZ file dataset which we can use for training. deepBlink create requires two inputs. First, the path to where your images are stored. Secondly, the labels. In our case, we save them to the same directory, so we have to pass in the same directory twice. Additionally, you can also change the name of your dataset, as well as the size to which all of your images will be cropped. You can also tune the test or validation split, but we won't be covering this in this video. Now, go ahead and type deepBlink create -i for input, and then drag and drop the data folder onto the terminal window. -l for labels, and then -n to change the name of our dataset to superduper data. A couple of seconds later, you should now have a new dataset file in the directory of your images, which you can use in the next step. For training, you will need your dataset MPZ file from the previous step. We will create a configuration file by using deepBlink config. You should now have a config.yaml file in your current directory. Open up the YAML file and change two things. First, the name, which is the path to your dataset file. We can also use relative paths here, so we will just simply type in current directory and the name of the dataset. Additionally, you will have to change save_dir, which is the output directory where your trained model will be saved. In our case, we'll just save it to the current directory. For training, we will use deepBlink train. deepBlink train takes in two arguments. First is config, which corresponds to the configuration file that we just created. Secondly, if you have a CUDA-enabled GPU, you can pass in the device number by using the -G or GPU flag. Start training by typing deepBlink train -c config.yaml. Go ahead and press enter and see the training process begin. Note that without a GPU, training will take significantly longer, especially for larger data sets. So please be patient and grab a cup of coffee or two. Once completed, you will now have a model H5 file in the specified directory that can now be used for inference on new data. If you do not have access to enough data, you can try using a couple of pre-trained models that are available. Note that these models were trained on benchmark datasets, so they might not perfectly mimic the real world. As time progresses, we will try to add more and more models to support as many use cases as possible. All models are available on Figshare, but it's easier to download them directly through the command line interface. Go ahead and type deepBlink download -l. This will list all currently available models that you can download using deepBlink. To download a specific model, you can now type in download -i as well as the name of the model. With a normal internet connection, downloading should only take a couple of seconds. You should now have your specified model in your current directory. We have come to the final step, which is predicting on new data. To predict, we will need two things. First, some fresh data to inference on, and secondly, a pre-trained model which either you created yourself using deepBlink train or downloaded using deepBlink download. We have this image that we want to inference on. Let's have a look at the help text for deepBlink predict to find out more. You will note a couple of things. There are two required arguments. First, the image input, and secondly, the pre-trained model. Note that the input can either be a single image or a directory containing multiple images. This greatly facilitates batch processing. If you want to measure the image intensity at each detected spot for further analysis, you can pass in the radius flag. As the name suggests, this will calculate the integrated intensity in the specified radius around your spots. If you only want the intensity at the single central pixel, the radius has to be set to 0. If your image is n-dimensional, you will have to pass in the shape of your image, which I will explain in a second. Now, let's go ahead and predict. Here, we will use this fish image and the model that we just previously trained in deepBlink train. Type deepBlink predict -i for input and the name of your image, then -m for the model and the path to your current model. As output, you will get a CSV file with the same name as your input image. If you passed in an entire directory, all of your CSV files will match the corresponding images. Let's have a look at how well it predicted by opening the output in Fiji. This visualization in Fiji will only work for 2D data without intensity, meaning without specifying the radius flag. Unfortunately, Fiji will connect all of our spots, but from a visual inspection, it looks pretty good. The output CSV file will always contain the X and Y position of each spot. Additionally, for n-dimensional data, or if the radius flag was passed, you will have further columns added automatically. Back to n-dimensional data. Let's say we have this image containing both a z and a time dimension. You might have to specify the shape to prevent confusion between different channels. The shape is simply the arrangement of your image's axes. To determine your image's shape, go ahead and type deepBlink check and the path to your image. As output, you will see your image's shape and deepBlink's best guess. If this is incorrect and time and z have been swapped, please specify the shape using the format described. After watching all of these videos, you should be able to train and infer on custom data. If any questions remain, go ahead and ask a question. Ideally, you can do this by creating an issue on GitHub or by asking a question in the comments below. Additional information can also be found in the wiki page on the GitHub repository. Thanks for watching, and I hope you enjoyed deepBlink.